You are given a list of numbers, say 16, 3, 19, 2, 81, 56. You are given this list of numbers and you are asked to sort it. Now, don't try to be much efficient, but let's try to solve it. Whatever comes in your mind. Whatever comes in your mind. You don't need to be very sophisticated. Can someone help me? How do I sort it?
Adjacent element comparison.
Yeah,
First,
that's one way. I'm trying to find. Okay, let's see what others think. We'll just ask a few opinions. So how do you sort it? So we are trying to sort it from smaller to like in ascending order. That means from smallest to the largest.
First,
Comparing the first element with the other elements and swapping it if it finds the other element is less than it.
Okay, we can do that. Okay, let's say what is the sorted thing? What is the sorted thing here? What will be the sorted result? First will be 2, right? Next 3, right?
3,
Yeah, 2, 3, and then 16,
16,
19, 56, 81,
81.
right?
81.
This is going to be the sorted result. Okay. So we already have like 2 solutions. One solution was, and I think both of you told us about the same solution. So what did you do? 16. You compared 16 with 3, right?
Yes.
Yeah.
And then, okay, so just don't try to say someone doesn't know any algorithm. Someone who has no idea about algorithm, can he sort this one? What will he do? Let's try to think like in a naive way. Say you ask your parent. Yeah, your parent also may know what algorithm says, but suppose he has no idea about this algorithmic concept, but still he can sort this, right? How will he sort this?
First, look for the smallest number.
Yes, he will look for the smallest element, right?
Yeah.
So that is the most naive way. So he will try to find the smallest of 16, 3, 19, 2, 81, and 56. What will be the result? 2, right?
2.
Okay. So to find this smallest element, how many elements he has to check?
N elements, 6 times.
Yes, n times, right?
Yes.
So number of operations, like number of numbers, he will try to check. He will check every number, right? He will check every number, and after he checks every number, only then he knows that, okay, 2 is the smallest, right? Okay, so next time what will he do? He will again try to find the smallest, but this time he will exclude 2, right?
Yeah.
So we'll cross it. And this will give him a result of 3, right?
3.
So how many elements he is checking now?
N minus 1.
N minus 1 elements, right? So he's now checking n minus 1 elements. Okay. Yes. So he will keep on doing this, right?
Yeah.
Next time he will get 16, right? And how many
Yeah.
elements he will check? Because this time 3 and 2, he won't consider 3 and 2 because these are gone. You just
N minus 2.
yes, n minus 2 elements. So n minus 2 elements you will check. So number of operations he is doing is kind of n minus 2. So he will keep on doing this, and the total number of elements he did inspect is n into n plus n minus 1 plus n minus 2, right? Plus
It will be n plus n minus 1 times. 2n minus 1 times.
yeah,
The
so
last,
it's like
Yeah.
finally there'll be 2 elements, right?
yeah.
And he's done. So it's like the series of the summation of the series, right? 1 to n, right?
Yeah.
So it's the total number of operations or comparisons or inspections he's doing is n into so there are like n minus 1 elements here. So n minus 1 into n minus 1 plus 1 over 2. So it's order of n square, right? Can we say that?
Yes.
So we found the most naive way of sorting, which anyone can do. Like you ask someone to find sort it, his brain will work like this. He will try to find the smallest element, then the second smallest element, and basically his thinking process is also some kind of algorithm. It doesn't matter whether it's an efficient algorithm or not, like a naive algorithm, but it still is some kind of process, thinking process, which is an algorithm, and this algorithm is order of n square algorithm, right? So the algorithm that we just solved here, we can say this is we can call it selection sort. Do you understand why this is selection sort? So that means every time we are selecting the smallest element, right? So every time we're selecting the smallest element, and this way, eventually the array is getting sorted, right? So this is how this is working. So basically, if I take the previous example here, so what I'm doing here is, you can think this algorithm is like this. So basically, first, I'm just selecting a minimum. So it's like so selecting a minimum. So 16, say I'm saying 16 is my minimum. And then I'm going here and checking, or let's say this is how this select, if I write it as an algorithm. So basically what my target is, next I have to put 2 here, right? Anyhow, in the next step, correct? So how can I do that? I can just try to find the smallest. So find the smallest. And then how can I put the 2 here? I can just swap, right? Find the smallest and swap. So that means next time it will be 2, 3, 19, 16, 81, 56, right? Okay. So that means I found the smallest element and swapped it with the first element. Is it clear to everyone?
Yes.
Okay. Next 2 is now permanent here, right? So next 2 is permanent. I start from where? Here, right? So my target is next time is to put the second smallest element here. So what I try to do is I try to find the second smallest element, which is the second smallest element. 3, right? But 3 is already here, right? So I don't need to do any swaps. Okay. Next 2 and 3 are permanent here. So I start where? I start here, right? Now I try to find the smallest element here. What is the smallest element in this portion?
16.
16, right? So what do? I
We
swap
have to
16 and 19, right? Because I want to put the 16 here, right? Is it clear to everyone?
Yes.
Okay, next time what is fixed? 2, 3, and 16 is done, right? My target is to put the fourth smallest element here. And for that, I work on which portion? This portion, right? And I already see that the smallest among these is 19. So I am done, right? I don't have to do anything. What is the next thing I'm doing? What is fixed now? 2, 3, 16, and 19 are done, right? I just have to work on what?
81 and 56.
Yes, and my target is to put it where? In this
56
position,
and
right?
81.
So for that, I'm seeing that 56 is the smallest. So what I do is I just swap it with the position, right? I put the 56 in the right position and 81 goes here, right? So now I am done. Okay. So in every step, what I'm doing is I'm finding the smallest element and putting it in its right position, right? So how I am doing it? By swapping it, right? Okay. So let's see. So is it clear to everyone? Okay. So for that, in the first case, I have to check all the n numbers, right? In the second case, 2 is fixed, so I am checking n minus 1 numbers, right? In the third phase, I am trying n minus 2 numbers, right? So eventually, it's going to be order of n square. So it's the same algorithm that we actually talked about this. So it's the same thing. Just I'm trying to be a little bit more formal here. So we are finding the smallest element, putting it in the leftmost place. And then everything is unsorted. Then I try with the other n minus 1 elements, trying to find the smallest and put it in the leftmost, that is here. Then again, finding the smallest among these 4, putting it in its right position. Clear to everyone how selection sort is working? Okay. So now, tell me one thing. So if a number is, if you're given this 1, 2, 3, 4, 5, 6, right? You're given this input and someone tells you to sort it using selection sort. So what do? What is your target? To put the smallest element where? Here, right? That is your target, right?
Yeah.
So I want to put the smallest element here. So to find the smallest element, what do I have to do? Can anyone tell me? I have to go through all the elements, right?
Yes.
To find the smallest element. And then I find that, okay, 1 is the smallest. So I don't have to swap, but I'm done with 1, right? Next time, my target is to fill up this. So I know that. So my target is to fill up this location, right? With the second smallest. So what do I do? This time I check how many numbers. So to put 1 here, how many checks do I have to do? 6 checks, right? Okay. Now 1 is fixed here. What were the other elements? 2, 3, 4, 5, 6. So this time I have to check all these 5, right? And see what is the second smallest.
2.
What is the smallest here? 2, right? So to put 2 here, how many operations I had to do? 5 checks, right?
Yes.
Okay. So my point is, like, although this was sorted, although this was sorted, I didn't get any benefit. Did I get any benefit? Still, I had to do n minus 1 checks here, right? I had to do n minus 2 checks here, right? Next time I had to do n minus 3 checks. So in total, it would be like n minus 1 plus n minus 2 plus n minus 3, right? Which is order of what?
N square.
Order of n square, right? So that means selection sort is, even if you are given a sorted array, what is the complexity of selection sort?
N square.
Yeah, n square. So I can say even in the best case, it's order of n square. You are given a sorted array, but it's still, someone gave you a sorted array, but your algorithm still works order of n square times, right? Or if someone gives you an unordered array, still you need order of n square, right?
N square.
Clear? Okay.
Yes.
Okay, so let's go to the next algorithm. Next algorithm, I think some of you were saying that we can do some, yeah, let's go to the next algorithm. At the beginning, 2 or 3 of you were saying that we will do some kind of pair by pair comparisons, right? Okay, now let's go to that one. And that one is called bubble sort. We'll say how that is bubble sort. So let's go to that algorithm. Whoever said like we will do pairwise comparisons, can you help me with this? So first I will check 16 with what? 3, right?
Yes.
Okay, and since 3 is smaller, so I will swap 16 with 3. So next, in the next iteration, it will look like this. Then I will check 16 with
19.
19. So 16 will be in its position, right?
Yes.
Okay. Next, I will check 19 with
2.
2. So what it will look like? 3, 16, and then
2, 19.
2, 19.
yeah, 2, 19, and 81, 56, right? Okay. Okay, so I'm done with this. Next, I will check, I will go to this location, right? I'll check 19 with 81. It will still remain the same, right? Okay, next time I will check what?
81 and
81
50.
with 56. So what's going to happen?
16.
16, 81, right?
56.
56 and 81.
Okay, so after all these, what did I achieve? The largest element came here, right?
Yes.
The largest element came to the end. Okay? Just think about this. If the largest element was here, suppose this was 100, the first element, 100 would have traveled all the way to the end, right? Because 100 would have first checked with 3, 100 would have been here, then 100 was going to be checked with 19, 100 would have been going here, right? Okay? Is it clear to everyone?
Yes.
Yes.
So even if the largest element was on the leftmost, it would have propagated to the rightmost, right? So it's like a bubble. So if you are in a, say, if you are in a, you can think as a bubble. So a bubble actually, so you can think it as a big bubble. So if it's big, it will go, and go to the surface, right? The surface is here, okay? That's why it's called bubble sort. Okay, so let me ask you, okay, so far anyone has any question? So what did I achieve after all these? The largest element came to the right. So how many operations I did to get the largest element on the right? How many operations I did?
6.
6
One
operations.
comparison, 2 comparisons, 3, 4, 5, 5
6.
comparisons, right? So n minus 1 comparisons, right? N is 6. So n minus 1 comparison to get
I have a question.
the rightmost number right. Rightmost number sorted, right? So after n minus 1 comparisons, I got one number in sorted position, right? Next time, what do I have to do? Next time I have to start from here, right? Again,
Yes.
I have to compare what? 3 and 16 again, right? Nothing happens.
69.
Yeah, then I have to compare what? Again, 16 and 2, right?
2.
2 comes here, 16
2
goes
and-
here, right?
Yeah.
Then I compare 16 with 19. Nothing happens, right?
19. Yeah.
Oh, this is 56, sorry. Okay. Then I compare 19 with 56. Nothing happens, right?
56.
I'm done. So how many, so this is the second. So this is the first one. This is the second one. How many times we do, how many comparisons we do now?
4 times.
Minus 4 times. N minus.
N minus 2. I do one less comparisons, right? Because this time I don't go up to 81. 81 is already done. So I stop here. Okay. So n minus 2 comparisons to get the second largest number, right? So is it clear how bubble sort is working? Yes. Any question?
Yes.
So it's still how many operations I need? To get the largest number, I need n minus 1 operations, right?
1.
To get the second largest, I need n minus 2 operations, right? So I keep on doing this until I do 1 operation, right? So this is order of n square, right?
Yeah.
Okay. Clear to everyone? Does it make sense?
Yes.
Okay. Now I'm asking you if it's sorted. If I had given you a sorted number, 19, 17, sorry, 27, 63, 81. If you are given a sorted number, and if I ask you to sort it using bubble sort, or I ask you sort it and you use bubble sort, still you are doing this thing, right? You are comparing 1 with 16, nothing happens, right? Then you are comparing 16 with 19, nothing happens. 19 with 27, 27 with 63, 63 with 81, right? Nothing happens. So after all these comparisons, only you can say, okay, my largest number is here, right? Is it clear to you? So if I give you a sorted array, is it helping you? Like, is it reducing the number of comparisons or number of operations? Is it?
No.
No, it's not, right? So that means even if you are given a best kind of input, even in that case, your algorithm is order of n square, right?
Square.
And in the worst case is your array is not sorted. Even in that case, it's order of n square, right? Okay. so far, does it make sense to everyone? So we actually showed you two kind of sorting. The first one was selection sort. In the selection sort, in every step we selected the smallest element and put it in the left. Then we move the left to one place further. Again, we found the next smallest element, put it here. We move the left to this. We try to find the smallest element and put it here, right? So every time we selected the smallest element from the remaining elements and put it in the left. So this is how the selection sort worked. In the bubble sort, we just kept on comparing the adjacent elements. And if the right element was smaller than the left element, we just swapped it. So through doing this, what happened is the largest element would have just propagated to the end, right? But it's an order of n square algorithm. Okay. So far, all the sorting algorithms that we did is order of n square, right? Now let's try another algorithm. Let's try to, so the way we try to design algorithms is we try to find an efficient solution, right? That means, can we improve this solution? Can we do it faster? So far we have seen that all the sorting algorithms that we have shown are actually is taking order of n square time. So let's introduce you to a concept, and then we'll go from there. So let's introduce you to this concept, divide and conquer. So this divide and conquer is a type of algorithm, is a class of algorithms, as the name suggests. So are you familiar with the term divide and conquer? Not from, it may not be from the algorithmic perspective, from any other perspective. Anyone?
Yes.
Yeah, okay, give me just any example of divide and conquer. If you have heard this term anywhere, it doesn't need to be in math or science, anywhere. Have you heard this term?
Like
Yeah, someone is saying something.
like if we are doing any task, we'll divide the task into different parts and we'll try to solve it. So like
Yeah,
that.
so that might be helpful, right? So divide the task into smaller tasks, and then conquering means then put them together, right? Yes. So that is the divide and conquer, as the name suggests. So suppose you have an algorithm which has a complexity of n square, okay? That means if the input size is 100, how many operations I will need? 100 square, right? 100 square is 10,000. That means it will not exactly 10,000, order of 10,000. It might be 40,000, 50,000, right? So if the algorithm that you are solving is an algorithm of big of n square algorithm, for an input size of 100, how many operations you will need? In the order of 10,000 operations, right? Is it clear?
Yeah.
Okay. Now divide the input into two halves. That means 50 and 50. Okay. Now run the algorithm on the first 50. How many tasks, how many operations will be there?
50 square.
50 square, which is 2,500, right?
Yes.
Okay, so for the first 50, there will be like 2,500 operations. For the second 50, there will be another 2,500 operations, right? Clear? Using the same algorithm, right? So in total, how many operations you're doing? 5,000, right? Now you are not done because you have solved half of the problem here and half of the problem here, right? Now to solve the whole problem, now what do you have to do? You have to combine the two results, right? So 5,000, now I have to combine the results. This combine is a conquer part. So this combining will also take some number of operations, right? Okay, so combining the two results. So do I know that how many number of steps are required to combine the operations? I don't know, right? It might be 100 operations, it might be 1,000 operations, right? Say if it takes, say, so if the combining the results, say just as an example, combine the results take 100 more operations. So in that case, to solve the whole thing, how many operations I needed? 5,000 plus 100, which is how many? 5,100 operations, right? So can I say still is far better than the initial 10,000 operations? Is my like I am dividing it into two parts and then combining the results from two parts, and these took, say, 5,100 operations. Is it still better than the initial 10,000 operations? Yes?
Yeah.
Okay,
Yes.
so this is an example. But okay, now tell me, when is divide and conquer helpful? It's helpful if the combine step is not very costly, right? Say if the combine step needed 5,000 operations. If the combine step was itself needed 5,000 operations, did I get any benefit?
No.
No, right? In that case, the total number of operations would have been 15,000 because the combined part, that is, I divided the first part, second part, 5,000 operations. Then combined thing, if the combined thing, instead of 5,000, say 10,000 actually. If the combined thing was like 10,000, then the total number of operations now would have been 15,000. So I'm not getting any benefit. So just I'm trying to say is, if your combined part is like efficient, then the divide and conquer is helpful, right? Clear? So that is the thing. So what I'm saying is, it is important that the combining cost is, sorry, the combining cost is not too high. Okay? Okay. Now, so this, now let's say I have another algorithm which has a complexity of order of n. Okay? So if it's order of n for an input size of 100, how many operations I will need? Can someone tell me if it's an order of n algorithm?
100.
Yeah, it will require an order of 100 operations, right?
Yep.
Yeah. So if I divide it into 50 and 50, how many operations I will need for the first half? Order of 50, right?
Yes.
For the second half, I will also need
50.
50. So 50 plus 50 is already 100, right? So that means I still need 100 operations, and then combining will need some more operation, right? So basically, it's not going to help, right? Because previously I needed 100. Now I already, after division, I still need 100, and then combining will help, will add some more, right? So not
Yes.
all algorithms will help with divide and conquer. That is the point I'm trying to say. Okay. But an order of n algorithm can improve complexity only if some parts of it can be thrown. So we'll actually talk about this later. The point I'm trying to say is divide and conquer sometimes may help if the combined part is not too costly. And depending on like what kind of algorithm initially it was, suppose for order of n squared, it looks like it may help if the combining cost is low, but for of an order of n algorithm, is very unlikely to help with divide and conquer thing. Okay. So this is the theory of the thing. Now we will use one of these divide and conquer algorithms to solve the sorting thing. We are trying to improve our sorting algorithm. So far, what is the complexity of the sorting algorithm? So far, the sorting algorithms that we discussed, what is the complexity of that sorting algorithm that we have discussed so far? What was the complexity? Can anyone tell me?
N
Order
square.
of n square.
Yeah, order of n square, right? So it was order of n square algorithm. So what is a better algorithm than this? Order of,
N.
yeah, order of n is better. Is order of n log n better?
Yeah. Much better.
Yeah, n log n is also better because n log n is
It is
smaller
n
than
log.
n square, right? Right? If I try to find a order of n log n algorithm, still it would be much better. Okay, is it clear to everyone why n log n is smaller than n square? Because log n is smaller than n, right?
Yes.
Yes.
So let's do this. Let's try to do a merge sort. So this is a divide and conquer algorithm, which is known as merge sort. This divide and conquer algorithm can be is a class. So an algorithm that divides makes the problem smaller, solves the smaller problems, and then keeps on combining to get the result is a divide and conquer algorithm. And one such divide and conquer algorithm is merge sort. Okay. So let's look at the combined part. Say you are given okay. Let's see. Say you are given two sorted arrays, 3, 9, 15. Okay, and then your another sorted array is 16, not 16. Let's say 2, 10, and 13. So both of these are sorted, right? So if I tell you that to find a, how many elements are here? 3, right? This one also has 3 elements. If I tell you to merge these two into one sorted element, how many operations you need? I tell you to merge these two things and get a merged sorted thing. What do I do? Can anyone tell me how will you proceed to merge these sorted things to create one sorted list?
So that will be.
Everyone think, how can I use these two sorted to create one sorted list?
This will be
I will compare between which and what.
for the first element, which is 3, with all the 3 numbers of second list.
Do I need to compare with all 3? Because it's
All
already sorted, right?
second list, like all numbers of second list, right? But like in some cases,
Yeah. In some cases, you can
Yeah.
say that, okay, I got it. But can I
Negative.
say that the smallest here would be either this or this?
Yes.
The smallest here is going to be either this or this. Can I say that?
Yes.
Yes? Okay, so is it clear to everyone that the smallest here, to get the smallest here, I can just compare the first two elements. And then only these two elements are the candidates to be the smallest element. Is it clear to everyone? Can any other element be smallest except these two?
No.
No other element can be smallest except these two. So these two are the only candidates to be the smallest, right? So I can compare the first two elements and immediately I can say that 2 is the smallest element of the whole list. Can I say that?
Yes. Yeah.
Yes? Okay. Now tell me which are the next candidates of the smallest element?
3 and 10.
Yeah, can I just compare 3 and 10 and immediately decide that 3 is the smallest?
Yes.
Yes, right? Then this is gone. I move to 9. Next time, can I say that between 9 and 10, obviously something would be the next smallest? Yes? Because
Yes.
once I am done with the left ones, right? Those are actually gone already. So the smallest will be always on the edge, right? Either
Yes.
9 and 10
Sir.
is going to be the smallest, right? 9 is gone. Next, what do I compare? Next. What are the candidates to be the smallest one now?
10 and 15.
10 and 13.
10 and 15.
And 15.
Okay. You are looking at, because you are seeing this 13, it looks, 13 is not a candidate because 10 is already there, right? If someone was going to challenge 10 was here, say, just I'm giving a theoretical number, 9.5, right? Only that thing could challenge 10. Nothing else could challenge 10. 13 has no chance of challenging 10, right? That means only the next smallest one will be must be among 10 and 15. 10 is gone, right? Now what is the next smallest candidates?
15 and 13.
15 and 13,
15.
right? 13 and then 15. Is it clear to everyone? So how many comparisons we need in total to get the merged list?
6 operations.
6 comparisons, right? That means 3 plus 3. So 6 comparisons. So after each comparison, I got one decision, right? Is it clear to everyone?
Yes.
Yes, sir.
Okay. I guess this is clear to everyone, but a few of you may still not be convinced. Let's try with another example and then you will be very much convinced. So say 1, 2, 3, 4, 90. This is the thing. And then say 15, 16, 18. Okay, so these two are sorted, right? So total, how many elements we have? I have total 7 elements, right? For no, 8 elements.
8.
elements.
Yeah. Okay, now if I want to merge, what are the 2 elements that are candidates to be the smallest?
1 and 15.
1 and 15, right? I can say for sure that among these two, one is going to be the smallest. 1. Done. After 1 comparison, I got 1 result, right? Next, what are the 2 elements that are the candidates to be the next smallest?
1 and 15.
15 and 2.
15 and 2, right? Because 1 is gone. So whichever is gone, I move it to the next. Okay, 2 is here. Next candidates,
15 and 3.
15 and 3, right? 3 is gone. So I move the candidate,
15
next
and
candidate. 15 is still the candidate, right?
Yeah.
So I'll go to 4. Now, next candidate, 15 and
90.
90.
90.
This time 15 comes here, right?
Yeah.
Next candidate, 15 and
16 and
16 and
90.
90.
16 and 90. 16, right? 16 is gone. Next candidate,
And
16, 18 and
90.
18 and then 90. So how many comparisons I total needed? 7 comparisons, right? 6 comparisons.
Mm.
So total 6 comparisons, and I get the, what do I get? I get a merged list. So can I say that if I am given 2 sorted lists, of total size n, creating a merged sort list needs how many operation? Order of n operations. Can I say that? So basically I need n minus 1 operation to create one merged list out of 2 sorted lists, right? Is it clear to everyone? And does it make sense?
So are you taking the number as n, which is the combination of
Yes, combination, like,
the both
yeah,
list?
this is the combination total number of elements in two lists.
Okay, yeah, then it
Okay.
makes sense.
So basically I can do the merging in order of basically one less operation, which is n minus 1 operation, which I can say order of n, right?
Correct. Yeah.
Okay, so looks like it's a very good algorithm, right? Order of n algorithm is a good algorithm. So if we are given 2 sorted lists, you see very easily you can combine them just with n minus 1 operations, right?
Yeah.
So this is a very good operation. Okay, now let's go try to use this thing in my divide and conquer algorithm, that is merge sort. Okay. So let's say take this data. Okay, so this is your given input data, and someone tells you to sort this. Okay, now tell me, is it a sorted array?
No.
It's not sorted, right? Okay, So let's do the division part. Let's do this. This is not sorted, so I divided into two parts. Now tell me, is this part sorted?
No.
No.
No, right? This is also not sorted. Okay, so let's do this thing. Let's further divide it. I'm creating like 4 lists now, right? Okay. Now, some of these lists are sorted, but all are not, right?
Yes.
Okay. So let's further divide it. Into 8 lists. Now I have 8 lists, right? Small lists. Each of these lists have how many numbers? 1, right? Okay, now tell me, is this list sorted? This list, is this sorted? This is separate lists, not together. This is like first list, second list. I divided them, right? Third list, fourth list, fifth list. Okay, tell me if there is just one number, can I just say this is sorted or not?
Yes, sorted.
This is sorted, right? So now each of these are sorted.
Okay. So
Okay,
now the
now
will
since each
be
of these are
only one.
sorted, can I keep on start merging, right? So 5 and 9, can I merge?
Yes.
How many operations will I need?
2.
1.
Okay,
One.
so now, yes, it will need just one operation, one comparison between 5 and 9, right? Okay, now let's merge these two, 2 and 6.
6. 1.
So this is the merge part. I will write it. So this is the merge part. I started merging from here, right? And this part I just kept on dividing, right? Okay, and then merging 13 and 7. What would be the result? 7, 13, right? 13 was sorted, 7 was sorted. After one comparison, I can get this. Can I get this?
Yes.
Last one, 8, 32, right? Now I have, instead of 8, I have how many? 4 lists. And each of these are sorted. Can I say that?
Sorted.
Okay. Now let's sort these two. 5, 9, and 2, 6, right? So 5, 9, 2, 6. There are like 4 elements, right? In these two lists, right? So if I merge them, it will look like 2, 5, 6, 9, right? How many comparisons will I will need here? 3, right?
Yes.
So these had like 4 elements.
And -1.
So after 3 operations, can I say after 3 operations, I got to this, right? I showed you already how the merge works, right? Next one would be can move. Oh, okay. Move. Okay, next one would be 7. Tell me, 7. I'm just merging, right? 8,
13.
13, 32. How many operations we'll need to
3.
find this?
3.
3 operations, right? Okay. Let's move to the next one. Now I have two lists, right? So I need to merge this with this. How many elements in total? 8, right?
8.
Yeah, okay. Now if I want to merge, it will look like 2, 5, 6, then
7,
7, 8.
8, 9, 13, 32, right? How many operations I will need here?
7.
7 operations, right? Because there are like 8 elements. Got it? Okay. So the merge sort algorithm is, what did I do? I kept on dividing the array, dividing the list until I got to a list of 1 elements, right? Clear?
Yes.
Okay. I got to a list of 1 element. And then I could just confidently say, okay, this, since I have 1 element, these are sorted. Now using that like merge algorithm, I started merging, right? I merged the first 2, 3rd and 4th, 5th and 6th, 7th and 8th list, right? Now I have like 4 lists of 2 elements. From that 4 list, I come to 2 lists. From that 2 lists, I come back to 1 final list. And now I am sorted, right? So far, it makes sense to everyone? How we
Yes.
actually sorted the array?
Yes.
Yes,
Okay. Yeah, so far it makes sense. Obviously, now you have the question like, what is the time complexity? Why did we do this, right? Is it with a better time complexity, right? You have that question in your mind, correct?
Yeah.
Okay. Yes, now comes the, let's do the calculation, how the time complexity is working here. Initially, how many elements we had? N elements, right? Input size was N, right?
Yeah.
Then we divided it into N by 2 and N by 2 elements list, right?
Mhm.
Right? Here, what is the list size? 1, right?
List size, operation size.
List size. Each of these lists are size of
1.
1. Okay. So now tell me, how many times you have to, every time I'm dividing by 2, right?
Yeah.
So I'm dividing by, from N to, I went to N over 2 size list. From there, I went to N over 4 size list,
4.
right? So I kept on
Yeah.
dividing until I got to 1
1.
size list, right?
Yeah.
So how many times, how many steps I need, how many divisions I have to do, or how many steps are here, total number of steps to get to 1 size list? Or how many times I have to divide? Can someone tell me? From N size list, I went down to 1 size list. Every time I divided the list to half. So how many times I have to divide? Like these division steps. This is 1 division step, right? This is another division step. This is another division step. How many division steps I need to get to a list of size 1? Can someone tell me? From N, if I divide by 2, keep on dividing by 2, how many times I need to divide by 2 to get to 1? Anyone? Log N. Does it make sense?
Yes.
Or okay, yeah, but I guess to some of you it's not making sense, or is it making sense to everyone? So from 16, how many times do I have to divide to get to 1? 4 times, right? If my n is say 32, how many times I have to keep on dividing the list to get to a list size of 1? 5 times, right? Because
5
from
times.
32, if this is 32, next time I will have a list of 16 and 16. Okay, let me show you. Suppose your initial list size was 32. Next, we have a list of 16 and 16. Then we have 8, 8, 8, 8, right? Then we have
Yeah.
4, 4, 4, 4, 4, 4, 4, 4, right? Then 2, 2, 2, 2. Right? And finally, those 1, 1, 1, 1, 1, 1, 1. This is step 1, step 2, step 3, step 4, and this 1, 1, 1, 1, step 5. So can I say that we total number of steps that we have to divide it how many times? Log n times, right?
Mm-hmm.
Mm.
Clear? Is it clear to everyone? Just the division part needs log n steps.
Okay.
Mm.
Because I'm not doing anything except just dividing the list. I'm not doing any other operation. I'm just dividing the list, right? So log n
Mm.
operations, okay? Now from 1 to again, I back to n. How many steps are here? Again, log n steps, right?
Mm-hmm.
Log n steps from, so to get back from 1 to a list size of n, log n steps. But now I am doing more operations, right? So I'm
Yeah.
doing log n steps. In log n steps, I come back here, but every time I'm doing more operations. Suppose here, say this is 4 elements, right? So can I say that, or just think like this, there are like total 8 elements here, right? In this step, can I say there are like 8 elements? Just think about this one. There are 8 elements, right? How many operations I need? 7 operations, right? So can I say that in this step, I needed how many operations? N minus 1 operations. Can I say that?
Yeah.
Yes.
In this step, I needed N minus 1 operations. Okay. In the previous step, how many operations I needed? Can I say I needed, so the list size was N by 4 here. Can I say it was N by 4 here? N by 4 here, right? N by 4 here. N by 4 here, right? Okay, so in total, how many elements were here in these two lists? N over 2 elements, right? Can I say that?
Yeah.
Okay, so if there were like N over 2 steps, can I say that to merge them, I needed N over 2 minus 1 operations? Can I say that? Because there are like N over 2, total number of elements in these two lists were N over 2. So to merge them, I need N over 2 minus 1 operation. Can I say that?
Yes.
And also I needed N over 2 minus 1 operation for this one also. Can I say that? Yes?
Yes.
So in this level, how many total operations I needed? N over 2 minus 1 plus n over 2 minus 1. That means n minus 2 operations, right?
Mm.
Yes, sir.
Can I say that?
Yes.
Okay. So now how many merge steps we had? We had 1 step, we had 2 steps, and then we had 3 steps, right?
Mhm.
Can I say that, okay, now we found that we had in total n minus 2 merge operations here, n minus 1 merge operations here. So just to simplify things, can I just say I had n operations here, n operations here, n operations here, something like that? Can I say that?
Yeah.
I can increase the number of operations because as I said, if you need say 7 operations, you can say tell someone that, look, I didn't need more than 8 operations. You are not lying, right?
Yeah.
Yeah. So if you need n minus 1 operation, still you can say, look, I don't need more than n operations. Still you are right, right? Order kind of thing. So you need n operations here, n operations here, n operations here in each step. And how many steps you have?
3 steps.
Log n
Log
steps.
of log of n steps.
Yes. So how many steps will be there? Log n steps, right?
Yeah. N log n will be.
Yes. So total number of operations. I have n operations here, n operations here, n operations here. So I'm telling someone, look, I have a algorithm which has log n steps, and in each of the steps it does n times work. So what is the total number of work?
N log of n.
N each, yes, n log n, right?
Yeah.
Got it?
Yeah.
Yeah. Now your question might be, okay, so this is just for the merge part, right? For the merge part, I did n log n. What about the division part, right? Well, in the division part, I just did
Log n.
still I did like n log n. So I didn't do much. So I divided it log n times, right?
Yeah.
So that is actually, yeah. So in total, it would be order of n log n. So using this division and conquer technique, using merge sort, I am doing it in order of n log n operations, right? So this is the time complexity of my algorithm, right?
Mhm.
Okay, so did we make an improvement than the previous sorting algorithms?
Yes.
Yes.
Yes. Previously it was order of n square. Now it's order of n log n, right?
N log.
Clear? Yeah. Now there is some, obviously there is some other costs, like we had to use extra space. We will talk about that later. But for now, using a divide and conquer method, we introduced an algorithm, merge sort, which improved our sorting algorithm from order of n square to order of n log n, which is a big improvement, right?
Mhm.
Huge improvement, because see, if it was, suppose if n is 100, n square is how much?
10,000.
10,000, right? N square is 10,000, whereas n log n is how much? 10 into, what is log 100? Can anyone tell me what is log 100? What is the value of log 100? That means 2 based log.
2.
Stu,
Hmm?
2 log 10.
2,
Log 2.
Okay, this way, like how many times you have to divide 100 to get to 1? 50, you divide it once, you divide it twice, you divide it thrice, you divide it 4 times, 5 times, 6 times, 7, something like 7, right? So log 100 is 7, right? Can we say 2 to the power 7 is the nearest to 100? 2 to the power 7, how much is 2 to the power 7? 128, right? 2 to the power 6, 64, right? So can I say that log 100 is 7, right?
Mhm.
Instead of 10,000 operations, now I need only how many operations? 70 operations.
70.
That's a huge improvement, right?
Yes.
Yes.
Yeah.
Okay. Okay, so that's it for today. We had a lengthy class, but I don't know, like, did it feel a little bit complicated?
Yes, bro. Hey.
Okay, but okay, so I think you have to go over the lecture. And if you have any confusion in anything, as I said, like try to create your own discussion group and ask each other. And if you still have confusion, just email me, okay? But yeah, so today we actually, in the initial part, we talked about Big O and time complexity. We solved some of the, looked at some of the codes and tried to find the time complexity. And in the second part, we talked about the sorting algorithms, right? Sorting algorithms are very important. You will actually use them very frequently. And what is the final conclusion? What is the best sorting algorithm? What is the time complexity of the best sorting algorithm, you know? Order of?
N log n.
N log n, okay? Okay, so that's it. Thanks everyone for joining, and thanks for remaining until this late. I will actually keep on posting the weekly things from this week and try to follow those, try to start solving those, do brainstorming on those, and go over the lecture. And I hope things will be more clear to you, but please don't leave it for the for later, because the reason is from the next lectures when I will just say sorting would be a part of the thing. So probably I will be solving bigger problems, and just in one step we will say we will do sorting and then we'll do this, and immediately we'll know that okay, I'm doing sorting, so it's n log n. We will not actually go through it over and over again. So this will be something just installed in your mind. Okay, any sorting n log n. Okay, so yep. Anyone has any question before we leave? Okay, so another thing, next week we'll have an exam based on these first 2 lectures. I will announce the date tomorrow. Okay. And if anyone doesn't have any question, that's it for today. Thank you.
Thank you. Bye. Good night.
Thank you. Good night. Thank you, sir.